This is a video overview of our senior design project, recovering thermal energy from an internal combustion engine. Our group members consist of Matt Clark, Jake Viertel, Michael Weinert, and Guillaume Pineau, while the advisor that's been guiding us through this design process is Dr. Wulandana. This video will touch on the need for this project, the design process endured, as well as the engineering principles we learned in our coursework that was employed during the project.
Internal combustion engines are the most popular and commercially available engines in the world. They intake fresh air and exhaust it at a much higher temperature. Their most common applications are in automobiles, lawn equipment, and snowblowers. The hot exhaust is a large amount of potential energy that is being wasted as it's dissipated to the atmosphere. The importance of this project is to prove that hot exhaust gases can be repurposed into more usable energy to increase the efficiency of IC engines.
A large amount of thermal energy is lost to the exhaust system. This system is necessary to remove byproducts of burning fuel. However, in doing so, a large amount of thermal energy leaves the engine and is simply dissipated into the air. In fact, a study in 2013 found that nearly 50% of energy produced by an internal combustion engine is lost to the exhaust system. This exhaust heat energy has the potential to be recovered and repurposed. This project accomplished just that through the use of a simple Rankine cycle, which converts the exhaust heat into steam, which was then used to power a turbocharger. The recovered thermal energy for turbocharging? Turbocharging is a great way to improve both engine efficiency and performance with just a small energy input. This is easily explained in the figure to the right. Here we have two engines by the same manufacturer. One is a naturally aspirated V6, meaning that the intake is at atmospheric pressure. The other is a turbocharged four-cylinder, so the intake is pressurized to above atmospheric by the turbocharger. They both make roughly the same power output, but since the four-cylinder has less cylinders, there is less friction and less fuel being burnt, so it is more efficient. This is the benefit of turbocharging, increasing power while still retaining efficiency. Demand for increasing engine efficiency. The automotive industry is trending with higher efficiency vehicles, which makes sense. People want to save money on gas and feel good about not burning as much fuel. Furthermore, the government has even set regulations that are becoming more and more strict regarding fuel consumption. This pushes engineers to develop new ways to boost engine efficiency, like through the use of turbocharging. However, current turbocharging methods induce a back pressure in the exhaust system, which the engine has to overcome. This project presents an improved turbocharging technology that is operated using steam generated by exhaust heat. This system does not generate any back pressure and creates no additional loss in the engine, since it utilizes energy that is already being lost. Requirements and constraints were noted. In order to successfully be applicable to a real automobile, this design must not hinder the functionality of the vehicle. It cannot increase the weight too much, it cannot take up too much space, it cannot cause any potential harm to the user, and lastly, the system shouldn't make the vehicle any more difficult to use. There are also a few uncontrollable physical limitations that must be accounted for. The device must be able to work with limited amount of exhaust heat produced by the engine. The steam pressure generated must be large enough to overcome pipe losses. And lastly, all construction material for this device must be able to withstand the high temperatures of steam.
Many of the courses taken in the mechanical engineering curriculum were implemented for proper analysis and development of the project. Thermodynamics and fluid mechanics were crucial topics when analyzing the steam through the system, while heat transfer and FEA were mainly used in the boiler. Software skills acquired through these courses were also very important, such as SOLIDWORKS to create our 3D modeling prototypes, and EASE to fully understand the temperature and pressure variations with the help of parametric studies.
The system was divided into separate components to be analyzed. In the boiler, a stress analysis was done to make sure the stresses due to pressure in the tank did not exceed the material limits. Heat transfer was modeled from the exhaust system to the water in the tank. A Rankine thermodynamic cycle was done to model the power to the turbine. Compressible flow analysis was done for the system. Intercooler heat transfer was done to model cooling of intake air, and a turbocharger thermodynamic analysis was done to predict intake pressure.
The design process began with a simple sketch showing the flow paths of the system that we are designing. With the sketch as a guideline, the flowchart to the right was created and shows each of the systems in the project, including the boiler that is to be fabricated. The boiler design process began with a sketch highlighting the main function of the boiler, which was to transfer heat from the exhaust gas to an enclosed water source. Utilizing SOLIDWORKS, we created a simple 3D model containing an enclosed tank with piping going through it. This design was improved by utilizing available materials such as copper piping and fittings, as well as a fire extinguisher as the pressure vessel. This design was further improved with the correct tank dimensions once the tank was acquired and a reduced quantity of fluid tubes due to the previous design's incorrect dimensional values. This final CAD model was then used as a guideline for the fabrication of the first physical prototype of the boiler. This prototype involved silver soldered copper piping, which proved to be inadequate for the temperatures reached in this system. With this setback, a second boiler prototype was created using steel piping, which was MIG welded together, providing great results. The boiler connected to its corresponding subsystems can be seen figured on the right. This final assembly can be seen in the figures on screen now. The fabricated boiler in orange can be seen attached to the turbocharger, which is at the top of the assembly, with the supporting lubrication system shown to the left. The onboard 12-volt electrical system can be seen to the right, containing an alternator ran by the output shaft of the engine, as well as a battery. Measurement instrumentation, such as pressure gauges and tachometers, can also be seen figured here. The boiler fabricated in this project provided great results, generating 30 psi of steam purely on waste heat from the engine. This is due to the high temperatures and mass flow rate of the exhaust leaving the combustion chamber of the engine. The resulting efficiency increase of the engine was minimal due to an oversized turbocharger creating little to no positive pressure. Reducing the size of this turbocharger will generate a higher intake pressure, resulting in a greater engine efficiency.
Throughout the year, we faced many challenges that we were forced to overcome. As a group, we faced our first problem when our initial boiler prototype failed. This initial failure prepared us for the long year ahead. Determined to complete the project, we quickly found solutions for our mistakes. The biggest hurdle that lasted throughout the semester was limited budget. With no stakeholders, companies, or sponsors, we had to find creative and ingenious ways to build our project. The engine used was taken from a broken snowblower found on the side of the road, and the boiler prototypes were built from emptied and clean fire extinguishers. In total, the group saved a little over $1,000 by repurposing materials. Finally, the unexpected breakout of COVID-19 caused some complications, especially in group meetings, which were overcome by using excellent team coordination.
The boiler on the final prototype has mild black steel piping. This led to significant rust on the piping system. Using galvanized steel would cause less rust and ensure maximum heat transfer and power transmission. The boiler system could also be expanded to simulate a closed Rankine cycle. By adding a condenser, there would be no need to constantly add water, and engine efficiency would increase, but would increase the amount of parts required and the complexity of the design. The cooling system also needs a complete redesign. The intercooler came off a 2019 Range Rover that was in an accident and is not being used correctly. It is removing a negligible amount of heat. Liquid cooling with a separate cooling cycle circulating engine coolant would do a much better job controlling the temperature. Finally, in a perfect world, an entirely different engine would have been used. This prototype was fabricated using a repurposed single-cylinder carbureted engine. In order to realize the potential of this design, a direct injection automobile engine is preferred.